we spent a fair amount of time in talking about relaxation in solution and developing red field theory and then talking about chemical exchange. And of course, part of relaxation theory is to get estimates of the rates, you can decide if some experiment is going to work. How do you set delays to optimize magnetization transfer forever, for example? There was a time back at the start of structural genomics when there was a big effort to do lots of NMR structures in solution. It's like there's a big effort to do a lot of X-ray structures. It was thought that it would make a huge difference if people had estimates of relaxation rates and could then, for a given protein, tune the delays very precisely. And that turned out not to be as useful because for the most part, the delays are such that, as you saw in the one problem set, adjusting these delays to be about 80% of optimal tends to be fine. The sine curves at the top are kind of flattish, so a small difference doesn't end up making such a huge effect. It actually turned out to be more useful is to design sequences that enable the recycle delays to be shorter so that you spend more of your time actually signal averaging data rather than waiting for magnetization to recover. And for example, a lot of the backbone triple resonance experiments, even if one uses deuteration, unless you use, or I should say, for a protein, if we wanted to do backbone triple resonance experiments, the critical hydrogen to deuterate is the alpha hydrogen, because that dipole interaction just causes all C alpha magnetization to relax very quickly. But if you grow E. coli in D2O, you get very highly efficient wash-in of deuterons to the H alpha position, but you leave some residual methyl protons around. And whereas if you want to really deuterate heavily, for example, doing methyltroses, then you have to use carbon deuterated glucose or other carbon precursor. But if you can afford to have some methyls around that are protonated, those are useful in shortening the recycle delays, because normally at the start of acquisition, you will have saturated all the proton magnetization. And the last thing you do is have some proton 90, so that any Z magnetization ends up in the transverse plane and is usually dephased by some gradient if it's not to be reported. So that the start of acquisition, the start of the recycle delay, you're starting from zero magnetization, and then you have to get recovery. And as we talked about in the Solomon equations, that can be slow if all the spins are saturated, there's no spin flips available. Whereas if you use some selective pulses in the sequence or incorporate some selective pulses in the sequence, or where it's possible to leave then some of the methyl proton magnetization on the plus Z axis, then you can get spin flips that help restore, say, the amide hydrogen magnetization towards Boltzmann equilibrium at the expense of the methyl magnetization. But of course, you don't really care about the methyl magnetization. You want to get started on the next backbone experiment. So these kind of longitudinal relaxation enhancements in practice have kind of turned out to be more useful than trying to fine tune the inept delays, for example, for a particular protein. There are also family of sequences that we have been talked about to try to address the problem another way. And that is for 1D experiments, it's been known a long time that for optimal signal to noise, you shouldn't start if you're doing a 1-pulse experiment. You shouldn't start with a 90-degree pulse. You should start with a pulse that has a flip angle less than 90. And the optimal flip angle is called the Ernst angle. And it's a function of the T1 of the protein. So that the idea is that you leave some of the magnetization on Z. So it's already there with the start of the recycle delay. And then the question becomes, then it's just a calculus optimization problem. If I'm trying to get the most signal to noise per unit time, I have to balance how much transverse magnetization I generate versus how long it takes to recover to Boltzmann equilibrium. And that can be solved. So for 1-pulse experiment, if you know T1, you can adjust the angle appropriately. And if you've ever had the misfortune to acquire a 1D carbonyl spectrum, it's really a bad idea to do that with 90-degree pulses. And again, sometimes people even bother worrying about what the Ernst angle is because it's almost always between like 10 and 30 degrees, so somebody will just pick a number. But for carbonyl carbonyl 1D direct detect, it really makes a huge difference. It's easy to go to the spectrometer and convince yourself of that. It's trickier in 2D experiments or 3D experiments because you have all these pulses mixing up all the magnetization. So in many cases, trying to adjust to something equivalent to an Ernst angle doesn't have a known solution, but there are subsets of experiments, mostly based on HMQC experiments, because the HMQC experiment, like the simple one, just has a proton 90 and then a proton 180. And there you can imagine designing an Ernst angle type pulse, right? Because if the 180 wasn't there, you would just say, I just have the Ernst angle pulse. In the presence of the 180, it's going to invert all the magnetization. So you really want to have the Ernst angle pulse minus or plus 180 degrees, so that then the 180 flips you back, so you end up at the Ernst angle. So these are called so-fast experiments. So fast HMQC basically has no recycle delay at all. And then there are variants of those. But what it's meant, of course, in practice is the real interest in relaxation rate constants is learning about dynamics of proteins. We talked some about the spectral density functions, et cetera. And what today's lecture will be about just some practical aspects of how people do these experiments in solution, at least on proteins. And when Hashim comes in a couple of weeks, you can find out from him how they think about these issues for RNA or DNA molecules. So there's just a few old review articles. And here are, some of the things that we've already talked about. At least today, I'm not going to talk about amide proton exchange or averaging of couplings, and particularly averaging of dipole couplings, and become an important technique. So we probably should say something about it sometime other than today. Amide proton solvent exchange used to be super popular, and then to some extent, maybe relaxation dispersion experiments have taken over from it. But with relaxation dispersion experiments, we're always really proud of ourselves if we measure populations, of 0.5%. But amide proton exchange, you can measure or detect minor states of 0.01%, 10 to the fractions of 10 to the minus fourth-ish. It's incredibly sensitive, but at least in proteins, the situation can be different in nucleic acids because of the pH dependence of exchange. In proteins, you're kind of limited to getting an equilibrium constant, never any rates. Of course, equilibrium constants are nice things to have. So probably a little underutilized today. So why do this? We can skip that. And here's a slide everybody shows as to what can be measured. And we saw that R1, R2 NOE, relaxation interference. These are dominated by overall tumbling in solution. So once you randomized all orientations by tumbling, you tend to be insensitive to internal motions that are slower than that. Once all memory is lost, not going to be magically regained. So for us in solution, that means the cutoff is somewhere in the low nanosecond range, tens of nanoseconds, and then somewhere in the low microsecond regime, these chemical exchange experiments, relaxation dispersion, start to pick up signal. And part of particularly what Christian Riesinger group has been doing over the last few years is trying to push this boundary down. Because certainly if we talk, a typical project would say, we have, say, the free protein and we measure some dynamics, and then we add a ligand and the dynamics go away. But we actually don't know if they go away or if they've just shifted into this window where we don't have any experiments. So trying to close down this gap is quite important. And then, well, here's amide exchange. And then, of course, eventually you get to real-time experiments where the dynamic process is slow enough, you can do some kind of rapid mixing in the NMR tube and just watch in real time collecting spectra over and over again. That's, of course, how most amide exchange measurements are done. And it can be done as well for other systems if things are slow enough. When we talked about 2D experiments, we said there was the preparation period, labeling period, mixing, acquisition. And the only thing that's different than most relaxation experiments is there's an initial block put in where the spin system relaxes. And then we record the effect of that relaxation on the ultimate signal. And this period might come before T1, it might come after T1. This could be expanded into a 3D experiment, but essentially preparation, labeling, mixing, acquisition, these are all the kind of blocks that we've already talked about, the NEP, HMQC, TOXI. And then the main issue then is the preparation has to prepare the spin system in such a way that we can interpret the relaxation time dependence. So in particular, fitting multi-exponential decays whose time constants are similar is extremely difficult. So we like to arrange the experiments in such a way that either the decay is single exponential or it's multi-exponential in a way that we understand. We might know the relative amplitudes of the two decays, for example, and can put that in as a constraint. Dave Case is a theoretician with a longstanding interest in NMR spectroscopy. He used to tell me that the problem with spectroscopists is they design very complicated pulse sequences in order to get a simple magnetization decay, as opposed to having doing what a theoretician would do, which was have a very simple pulse sequence and a very sophisticated data analysis approach. So perhaps particularly with machine learning, will be some changes. But here is, I don't remember if this was T1 or T2, on triose phosphate isomerase from years ago in my lab. And then some peak here, we measured the intensity as a function of T, and then you can see the single exponential decay. It's great that we all live in this building, because as time has gone on, getting data, more magnetic field strength has become more and more important, at least for solution. And we think now, for example, if you really want to fully characterize nitrogen-15 relaxation in solution, you need 3 fields, and 4 or 5 are even better. And there's not lots of places where you can acquire 3 to 5 different static magnetic fields. At least for highly quantitative measurements, aggregation is a gigantic problem for proteins. So high micromolar to low millimolar concentrations where solution NMR is done on proteins. Enormous number of proteins just have a non-specific KD for multimerization. And if you end up with some fraction of multimers in rapid exchange, and all the rates now are averaged between the multimer and the monomer. And for example, you're measuring T1, T2 to get order parameters. That's known from work that Mickey Schur did a long, long time ago, that this unrecognized aggregation tends to push the order parameters higher. And if you look in the literature, there are occasional papers where someone says our order parameters are higher than usual. We have a particularly rigid protein, but without really knowing that there's no aggregation, you don't know whether it's a particularly rigid protein or it's an effect of this oligomerization. Sometimes too, this shows up in profiles in which you see a very large number of residues that show chemical exchange broadening, 1 to 2 per second, kind of uniformly through the protein. And that's usually not some global dynamic process. That's usually either aggregation is making the fitting process, not proper, or the models don't include enough diffusion anisotropy. Anyhow, you can always dilute the sample and run an R2 and make sure that the R2s are independent of concentration. The joke in my lab usually is we measure R2, then we dilute the sample by a factor of 2. We measure R2 again, it's decreased. So we dilute the sample again, measure R2, R2 has gone down. We dilute the sample again, and now there's no signal. So it is a problem. And of course, if you're thinking about doing temperature dependence of dynamics to try to get ideas about activation, barriers, etc., the aggregation is also likely to be temperature dependent. So the amount of perturbation caused by the aggregation becomes a function of temperature, and can really swamp what it is you're trying to find. These days, most of the pulse sequences have in it what's called temperature compensation. So during the recycle delay, there are RF fields turned on to try to make sure that you deposit the same amount of RF energy into the sample, independent of what you're doing while you're measuring the relaxation decay curve. For example, if a Carper cell Nibum Gill experiment is being done, the number of 180-degree pulses during the relaxation period is changing. And then there would be dummy pulses in the recycle delay to make sure that there's the same amount of power going in. Of course, it can be tricky to figure out when to do that because you don't want those dummy pulses to be affecting your starting magnetization, because that then would be a systematic error. And then now most of the time these are set up in some interleave fashion to average over the entire decay curve whatever temperature effects there are, rather than collecting all the data for one data point, then the next data point, then the next one. Say collect all the given value of T1 over all the different T values, and then increment T1 and do that again, and then unshuffle the data to make the 2D experiments. It's particularly difficult, of course, as samples get saltier because then the heating effects get larger. Yep.
So if I'm doing an R1 dispersion experiment, then how do I control sample temperature between two RF fixtures?
Right. So then, in the ideal case, then you would, for example, say, I always want to make sure I deposit the same RF power as my strongest B1 field. And then when you're collecting with a smaller B1 field in the recycle delay, there has to be an RF field turned on to provide the missing power. And you can do the calculation, of course, of the relative field strengths. Of course, it's not being applied at exactly the same time, so it's not perfect, but it's kind of the best we can do. The other thing, modern Rooker spectrometers come with what's called a T-lock. So you can add a compound, usually some temperature stable methyl group, a compound containing a temperature stable methyl group. And then during the experiment, the spectrometer is constantly adjusting the VT-air to keep the splitting between the water line and that methyl group constant. So the water line is temperature dependent. So if there are temperature fluctuations, the VT gas gets adjusted. And that actually, is something everyone should be doing these days when doing these experiments, if the console supports it. And all the newer consoles support it. And surprisingly, spectrometer room temperature is important. Any idea why? All the solid state people should know why. Why would room temperature, the temperature of the NMR room, matter? You have the sample in solution that's thermostated by the VT air and the sample heater. And now I said we can turn on this temperature, this T-lock, which helps stabilize the temperature even more, but still the room temperature matters. So keeping it stable. But why would a stable room temperature matter if we can thermostat the temperature of the sample very well?
about the VT here itself?
That's that usually goes through a pre-cooler and then heated back up. That should be taken care of. The input temperature shouldn't matter very much. When you're tuning and matching a solid state probe, what do you care a lot about?
So does it have cryophone?
No, not yet.
Not here.
Isn't it the reason? Yes.
Yeah, this would be the same for cryoprobe or room temperature probe. Right? I mean, you worry about things like, do I have a quarter wave? Right, matching a quarter wave or half wave and things like this. It's kind of less, perhaps, critical in solution, but the same kind of principle applies. Once you've tuned and matched the probe, you've tuned and matched the electronic circuit, and that includes part of that is the coil and sample. So we're regulating the temperature there. But if you don't regulate the rest of the circuit temperature and its electronic properties change, right, then the tuning and matching will change with temperature. And if the probe is constantly going in and out of tune, then your 90-degree pulses aren't 90-degree pulses, and there's going to be some kind of error introduced by the temperature fluctuations in the room. And we actually can see this quite clearly. If you just collect a T2 decay curve on a day when the room temperature is very stable, and then come back one of the days where it's not stable, you can just easily see the additional scatter in the points just caused by this effect.
The solution probes don't use quarter wave matching?
It's tuned and matched to 50 ohms, but I actually don't know what that means relative to quarter waves, et cetera. We have to ask Ann these things. Every time I hear a solid state NMR person talk about tuning, they're talking about quarter waves, half waves. But you talk to a solution person and you say, I tuned and matched to, you know, until I got a minimum. Inside of the spectrometer console, Brooker tries to thermostat things very well. But the cables between the console and the probe are lying on the floor, and they're subject to the fluctuations. The small temperature changes that change the RF transmission properties of the cables, I think, are probably the main culprit in this. Because once you're inside the spectrometer, Brooker tries to keep things thermostated. And in the end, everything is about data analysis. As many duplicates as you can afford is great. And then proteins are, at the simplest level, proteins are simple things. They have secondary structure and they have a hydrophobic core. And luckily for us, and then 15 measurement of the backbone nitrogens tell us things about the secondary structure. And methyl groups tell us a lot about the hydrophobic core. And it turns out the best developed sets of experiments that we have are for the backbone nitrogens and for the methyl groups. It's very, very convenient. We know about spectral densities. We talked about Lopari-Szabo, talked about this. I don't know if I said anything about spectral density mapping. When analyzing the rate constants, as we saw, the rate constants are all these linear combinations of spectral densities. And then we have the model-free formalism or other way of analyzing the rates. So some program, say the model-free program that my lab wrote, you introduce, you tell the program the rates, and then it fits the model-free expressions to those rates. Of course, internally, it's calculating spectral densities, and then from the spectral densities, calculating the rates. But when it's looking at a quality of fitting, it's comparing predicted rates from the model to the measured rate. But another way of doing this is if you have enough data, since the relaxation rate constants are all linear combinations of spectral densities, in principle, you can invert a linear set of equations and get the spectral densities out, and then fit the spectral densities, and your figure of merit becomes comparison to the spectral densities, not to the original rates. And this is done both ways for nitrogen, depending on what group and what program. For the methyl relaxation, using the approaches developed from Lewis Kay's lab, where you're actually measuring deuterium relaxation in either CDH2 methyl groups or CD2H methyl groups. There, the number of spectral densities is relatively small. If you look at the tables at the end of one of the lecture notes, deuterium relaxation just depends on J0, J at the Larmor frequency for the deuterium, and J at the double quantum frequency for the deuterium. So a relatively small number of relaxation rate constants gives you enough data to invert those equations. The nitrogens, some of the rates depend on a larger number of spectral densities, right? The R2 for nitrogen depended on J0, J omega N, J omega H, J omega 0 quantum, J omega double quantum. So you have 5 spectral densities, and if you only have 3 measurements, R1, R2, and OE, you can't invert that set of equations without introducing some other assumptions. And in what's called reduced spectral density mapping, you make the assumption that all the frequencies near the hydrogen frequency, which would be the 0 quantum, the double quantum, and the single quantum J omega H, you assume that those are all high enough frequency that you're in this 1 over omega squared regime, so that they can all be modeled with one parameter that depends on a quadratic function of 1 over omega squared. And then you only have 3 unknowns, J0, J omega N, and this reduced J omega, effective J omega H. And then you can do it. So it's much more straightforward for the methyl groups. And this can be particularly nice if you have data in more than one field, because you can visualize the spectral density curve, which is nice, even if that's not what you're actually using as your fitting parameter. R2, of course, contains contributions from chemical exchange potentially, and it's usually helpful to have some idea if there is chemical exchange before trying to do the model-free analysis. And of course, if you have data in more than one field, then you can use the B0 dependence to try to check for chemical exchange, or as we talked about, the relaxation interference rate constants don't depend on chemical exchange because they're basically the difference in line widths between the multiplet components. Exchange affects both multiplet components the same, so the difference is independent of exchange. And perhaps it doesn't need to be said that one should pay attention to resonance offset effects. And this gets worse and worse as you go to higher and higher field. So here are some classic sequences for measuring R1, R2, and NOE in solution. It's already 30 years since Neil Farrow and Lewis K. published these. So I just would talk a little bit about, three sequences are very similar, so if we talk about one, it's enough, we'll tell you enough about them. So there's the sequence, and by now, hopefully, we recognize that this is just an inert block that transfers magnetization from the hydrogen into antiphase nitrogen magnetization. And then the next piece refocuses the antiphase magnetization into in-phase magnetization, and the final pulse puts the magnetization on either the plus or minus Z axis. And it's convenient to do that because, again, that will end up canceling the long time value, the NOE, so that the decay curves will go to zero. So we have one fewer parameter to fit when we do this. In the beginning, one tended to fit an offset, but that was really prone to ending up with offsets that were really the noise, not the real value. So in practice, it's always done this way, almost always done this way. And then here's the time period T where the magnetization is going to relax. And then the question becomes what to do during T so that the decay is as simple as possible, so that our data analysis is as simple as possible and hopefully therefore as robust as possible. And here we want to make sure that the decay is mono-exponential. But if you go back to the Solomon equation notes, most of what happens when you invert one spin in a two-spin system is that you get bi-exponential recovery because the two spins are interacting through the NOE. So this period here, decouple, is to basically then to eliminate the NOE. And when we did it in the Solomon equations, I said we can assume that the partner spin is saturated. And if we saturate the partner spin, then we'll have a mono-exponential evolution. But we also saw in those lectures that if we repeatedly invert one of the spins, we also quench the cross relaxation and get mono-exponential decays. And in the literature, historically, this was done both ways. So to saturate, you could just turn on a decoupling sequence like waltz and saturate the magnetization. Or you could turn on a series of 180-degree pulses. And for a while, they all seemed like they were basically did the same thing. And then Fabian Farage showed that it was slightly better to do a string of 180-degree pulses that were separated by 1 over J, 1 over the J coupling. So it's mostly done that way now, even though it says decouple, inside of this would really be a train of 180-degree pulses tuned to the scalar coupling. These gradients here, this first gradient here is to dephase any nitrogen Z magnetization, so that all the signal is coming from the hydrogen. These two gradients are just serving to clean up the effects of pulse imperfections of the 180s. This 180 here is going to dephase magnetization not attached to a nitrogen, including the water. And that can be perhaps not a good idea, because then you'll get saturation transfer from the saturated water to rapidly exchanging amides. So many new sequences might have selective pulses here to put the water back on the z-axis before the gradient to try to avoid dephasing the gradient. And same thing here, magnetization is back on, the magnetization we want is on SZ, so a gradient will dephase everything else. And again, whether or not that's a good idea depends on whether there's something in the transverse plane that you would rather first store on the z-axis. And same thing here at the end, this gradient is just to clean up everything except what's along z before frequency labeling and then transferring back for detection. So here, because our starting magnetization toggles between plus and minus, when we subtract the two signals, we'll end up canceling the steady state values. And the steady state values don't know about the initial values. And this is then a very standard sensitivity enhanced gradient selected HSQC sequence to record the signals. These T1, T2, and T3, we need to get back to antiphase magnetization. So this is just an inept plus the T1 period. So we want to evolve the J coupling here, but also label with T1. So this would be called a semi-constant time experiment, because these delays in the beginning, this is just going to look like an inept. And then as time goes on, the delays are both going to get longer and the positioning of the pulses will change. So we evolved the J coupling for an effective time 1 over 2J, and evolved the chemical shifts for an effective time T1. And I don't know if I have the numbers in the notes for that calculation. And then, of course, we could do this in a TROSY detection if we wanted. At this point, the experiment is over after capital T. How we detect the signal is then up to us. Yep.
Why are there so many net blocks towards here?
Right. So this first T1, T2, T3 is going to generate, right here, we have in-phase nitrogen. So this first block is going to frequency label with the nitrogen chemical shift and convert to antiphase. But that means here, right before 5,4, we have antiphase, say 2IZSX, that's cosine modulated with the chemical shift, and 2IZSY, that's sine modulated with the chemical shift. And this latter sequence has two inepts to refocus both of those. So we refocus one of them while storing the other as multiple quantum, then store the first as Z magnetization while we refocus the second. This brings down the Z magnetization to the transverse plane. And then this little gradient echo is to refocus the nitrogen magnetization that was dephased here. The little delta here is just long enough to hold the gradient.
So this is the preservation of equivalent.
Yes. But there's an extra inept in here, buried in here, because we're starting with in-phase magnetization. Yeah, so here just goes through what I said about the relaxation pathways. We have the R1 of the nitrogen, we have the R1 of the hydrogen. We have longitudinal two-spin order. We might have cross relaxation between all of these. And then some equilibrium values. And these are all things I told you about. And in the end, if we pulse fast enough, again, we're pulsing on the I spin. And you could say the effect of pulsing on the I spin is to make terms that have the IZ operator look non-secular with respect to SZ. So we could set these two terms to 0, these two terms to 0. And then we're potentially left with the cross relaxation between R1H and two-spin order. From the standpoint of measuring R1, we wouldn't care if these two were cross-relaxing with each other. The important thing is that we isolated R1 of the nitrogen from everything else. They're cross-relaxing. It doesn't matter. But these end up actually, it could be there still is an epsilon here. This could be a typo, not the double check. But certainly the secular argument isolates SZ from the other, so that's all we really care about. So there we go. And we have single exponential decay. There are more recent sequences. To me, they seem like they're yesterday, but now they're now a decade old from Advaxis group that are really excellent if the protein is deuterated. If the aliphatic sites have been deuterated. Here's some sample data. There's some results. I think I showed you some of these already. And then we talked about spectral density functions. Here are some, I don't remember how many examples I've showed you of real data. But here for ribonuclease H, we had dated 3 magnetic fields. So there's one value of J0, there are 3 values of J omega N, 3 values of this effective J omega H. And then for something that's pretty rigid, you're fit with a very simple model that just has an order parameter and an overall tumbling time. And the motion is so restricted and the internal time scale is so fast, we don't even see the internal time scale. And here's one that's a little more flexible. The order parameters dropped a little bit. And now there's an effective correlation time. And the dashed line would be if we set the internal correlation time to 0, and you can see the interesting result that the lower fields spectral density functions are fit exactly the same with and without the internal correlation time. And it's the hydrogen spectral density that tell us that there's an internal motion. And those are determined primarily by the NOE experiment. And the NOE experiment is the least sensitive experiment of all of these, because there's the NOE sequence doesn't start with an NF. We have to start with Boltzmann equilibrium of the nitrogen spin. So the sensitivity is way low compared to the T1 or T2 measurements. And that's a little bit unfortunate because it's so critical for determining the internal correlation times. And then here's a quite flexible residue. And now you can see there's two order parameters. And then in this case, an effective correlation time that is associated with the slower time scale process. So it's about a nanosecond. And again, you can see the dashed line is the simplest model. The dotted line is the model assuming a single order parameter and a relatively fast internal correlation time. And then you can see that it's really only the spectral density function at the highest magnetic field that distinguished the models in this case. And this was at 800 megahertz, 900, 1.2 gigahertz make this problem easier and easier to resolve. But it probably should tell you, the data is pretty sparse, and that limits kind of how complicated the models possibly can be. And as far as we know, the nitrogen 15 data recorded at high field has 5 bits of information in it, which means the most complicated model you can fit is an overall tumbling time, 2 order parameters, 2 time scales. You can parse those in different ways, but basically 5 is what you get. And that's because of this 1 over omega squared dependence that all the spectral densities have when you get the high magnetic field. To get somewhere, we have to get the lower magnetic field. And you can already see the problem right here. Our first point, here's J0. Our first points coming from J omega n are already roughly an order of magnitude smaller than J0. And all of these spectral density curves, right, have this profile that looks like this. They have this rollover where you get to the omega 1 over omega squared regime. So you really want to sample the rollover, and the rollover has already happened for these data. And to get below, I think this data was probably, was 500, 600, 800. For a decent sized protein, going to below 500 megahertz is pretty hard because of resolution and sensitivity. And the only solution is to do relaxometry, where you move the sample to lower field. You polarize at high field, go to low field for relaxation, and then come back to high field for detection. And we have a sample shuttle here on the 700 that can do that. And the current difficulty is while you're moving the sample up to the low field, it's relaxing. So that has to be put into the calculations. But of course, the point of the measurement is to measure dynamics. But to do the calculation, you need to know the dynamics. It's a kind of circular problem that is still not completely solved, for us anyway. But that's the limitation here. The limitation here is we've already dropped below this rollover point. There's what order parameters look like. Here's one of the first applications that showed ligand binding. So this is calmodulin, calbindin. Walter Chazen worked on when he was at Scripps. And here's the apoprotein, and there's the calcium loaded. So there's two calcium binding sites, one here and one here. And you can see not so much happens over here between apo and calcium loaded. And over here, there's a big increase in order when the calcium binds. And they had a mutant that blocked calcium binding here. And you basically had the same profile over here. Anyhow, this was the first case where then the change in order parameters was used to estimate a change in conformational entropy. At the time, we thought that this site was relatively rigid because most of the ligands to the calcium were backbone carbonyls, whereas here most of the ligands were side chains. So it seemed like this had to be a more preformed site. And then, I mean, this was done in the 90s, all of this work. And then a few years ago, Mark Rance was doing a simulation of calbindin D9K, mostly, I think, to look at methyl order parameters. But he noticed in the simulations that a sodium ion dropped into this site and ligated to the carbonyls. So some of this behavior, maybe all of it, this apparent rigidity is due to the fact that there's sodium in the sample. The sample had 100 millimolar sodium or so. Even if you try to get rid of the sodium, you have to go to extreme lengths to get all the sodium out of the sample. It was a big surprise to me when he told me there was a sodium sitting in this site in the simulations. So then, of course, there's chemical exchange experiments. Some fairly obvious points. So here is what's called a ZZ exchange experiment. So now, if you do a nosy, you put magnetization on Z, magnetization is transferred between spins from the NOE, but if there's chemical exchange going on, magnetization is also transferred between spins. So a nosy spectrum has NOE peaks in it, has exchange peaks in it, and they have the exact same sign. And I think I might have said at some point that then a rosy spectrum has opposite sign, and that's why people do rosies to look for chemical exchange. But these days, because we can label, using a nosy spectrum to quantify chemical exchange is difficult. Whereas if you can put nitrogen 15 in, then there's no nosy peaks confusing things. There's only the exchange peaks. So this is essentially a nosy for nitrogen 15. So there's an initial inept, which you wouldn't need for a hydrogen nosy. And then frequency labeling. And this frequency labeling simultaneously labels the nitrogen chemical shift and refocuses to in-phase magnetization. And then here, the magnetization is on the Z-axis. And then we read out. We can't do the sensitivity enhancement because we can only put one component at a time onto the Z-axis. So this is just a normal HSQC at the end. And again, there's decoupling for the same reasons we talked about before. This looks exactly like the T1 experiment, except the labeling is frequency labeling is before the delay, whereas putting it after the delay, we have the advantage, we can do the sensitivity enhancement. But here it has to be before, because that's how you're gonna get resolution. Yep.
I'm wondering if I can have a refilter to account for T1 relaxation.
In this sequence, if you mean during capital T, you would like to have only exchange and not relaxation.
Yes.
Then you would have to have basically a way of, for example, having a total period T in which part of the time for which T1 happened the whole time, and part of it you were able to turn off exchange. So you would have a variable delay where exchange evolved, and then T1 would happen the whole time. So T1 wouldn't depend on,
Yeah.
and
Is that being done?
I can't think of that being done. One would. I can't think of it,
Okay.
of it being done. Yeah, then of course, if exchange is relatively fast, there could be exchange during these delays, during the inept delays. You think, well, this is transverse magnetization, it's slow exchange, the sites are resolved. There shouldn't be cross relaxation because of the secular approximation, except you have the 180s. And the 180s are refocusing chemical shifts, so you can get some cross relaxation that you don't expect, even though you're in slow exchange, depending on the time scale. So sometimes this has to be taken into account. Julie Fagan and Nick Hudd had, I think, a quadruplex where they could see exchange as ions bound in the quadruplex was slow enough that even in the normal HSQC, no relaxation delay, they could see cross peaks. Kind of a very unexpected and cool result. The labeling gives the initial conditions then depend on the frequency difference, just like a nosy, same sorts of things. So here's some data. At low mixing time, we just see the two peaks. And then as the mixing time increases, we see the cross peaks. And most fitting software takes the 4 peak intensities as a function of time and analyzes them simultaneously using basically an equation like this. When Vesco Malusha was in the group, he showed you could take the 4 intensities and form this ratio, and that the ratio was compensated for differences in relaxation rate constants between the sites, and you ended up with a simple dependence that was the product of the rate constants and then the delay squared. And this was independent then of particular residues. So you could plot all your residues on one graph and fit one curve to get this product. The downside is you just got the product. So to deconvolute the product, you had to have the equilibrium constant, which meant you needed to record an HSQC in which the peak intensities reflected the Boltzmann populations. And that's not so easy because, of course, there can be different differential relaxation of the two sites if their R2s are different. So that by the time you get done with transfer, you've altered the peak intensities relative to Boltzmann equilibrium. But John Markley has a modified HSQC where you collect a series of spectra and can back predict then the exact equilibrium constant. And then you can separate these. That's all described in Yu Li's paper. Here, by the way, since we talked about relaxation interference, here's a sequence for measuring relaxation interference. You measure the signal two different ways. You measure the in-phase signal and you measure the antiphase signal. So we start at time 0 with just antiphase, and then because of cross relaxation, some in-phase magnetization builds up. And then we select one or the other by moving this pulse around, or these two pulses around. And then the ratio of the two builds up as a hyperbolic tangent. The hyperbolic tangent fit to the data gives the rate. Here it is for ubiquitin. And then the comparison pops out the exchange broadened results. Because again, effectively, the interference rate constant is the difference in rates between the multiplet components. It doesn't depend on exchange, but R2 depends on exchange. This here is, you might hope that the line looked better than having this little blob, but some of that is due to the variation in the chemical shift anisotropy from residue to residue, which is quite difficult to characterize in solution NMR. So this was all assumed, this is all basically assuming an average chemical shift anisotropy. The relaxation dispersion field was kind of reignited by this sequence that Pat Loria thought up, because what you would like to do is alter tau and see then how the CPMG rates vary as a function of tau. The problem is, as you alter tau, the amount of J coupling evolution changes, so that the J coupling effects are coupled in to the relaxation effects. And I wrote a paper as a postdoc that said that meant we couldn't do CPMG experiments on proteins. And then when Pat was a postdoc, he realized that all one needed to do is here we create antiphase magnetization. We're doing the CPMG on the antiphase magnetization. As a result of the J coupling, we build up some in-phase magnetization. And here we have a sequence that swaps in-phase and antiphase magnetization. And then we do the second half, so that we start with a lot of in-phase, build up a lot of anaphase, swap them, and then the reverse happens. And we come back as if the scalar couplings were averaged over the period.
Why couldn't you just decouple?
Well, now there are sequences that decouple. At the time, there's a problem, these delays are short enough that you can't fit a super cycle. Decoupling sequences usually come in super cycles that average out imperfections. So you couldn't put a super cycle in here and we had earlier shown when I was still a postdoc that trying to do that led to enhanced decays because the imperfections and the decoupling led to faster decay. These days, there are sequences where you turn on a very strong CW field, and that has to be very carefully calibrated depending on the delays and the J couplings. So it saves this relaxation delay, but adds a little bit of complexity. Yeah, so it's kind of historical. That's the purpose. Our relaxation matrix would look like this. We have the J couplings linking in phase and antiphase. The antiphase term has this contribution from the remote hydrogens, as we've talked about before. And essentially, if we go through and see what happens when we have this net-like period in the middle, we end up with an effective relaxation rate constant that's the R2, and part that depends on the tau period because of the J couplings. That's for one, but then if we do this U period and swap in phase and antiphase, then we end up just with R2 plus half the R1. And that's the penalty you pay. If you decoupled, right, you just have the R2. So the decay rate would be slower, which is nice. And then of course we would normally deuterate to make this even smaller. And here's just the math as a function of time. This is what one would see in the conventional CPMG, and then that's what you see in this averaging procedure. Here's the initial data that we collected. And but the intercepts here, this is 1 over the delay. So the intercepts should be infinitely long delay. So basically the free precession rate constant, and then should scale quadratically with the field. And that's kind of true here, not true here, definitely not true here and here. And in slow exchange, the exchange broadening is independent of the field. It's just the jump rate. So here, this looks like nearly field independence and therefore slow exchange. And here you're approaching fast exchange. It's nice to know the plateaus here. In these data, the plateau value, just the R2 naught from dipole and CSA, was a fitted parameter. And sometimes that plateau is pretty well determined and sometimes it isn't. And there's now experiments like this heroin experiment from Christian Griesinger for estimating R2 naught. So that becomes a known rather than a parameter you have to fit. And then one can get out chemical shifts, try to do modeling, etc. And these days, since one does this more with CES, you can get a very large number of chemical shifts and then use those with programs like CS Rosetta to try to get structures of the alternate conformations. This was the first example of trying to do that basically from a database. And given that we're at 2:30, maybe I'll leave R1 row relaxation for the next time I'm here after the ENC, so that we don't rush through it, and so that I can get to the airport. Any questions? Oh, yeah, tomorrow, because I'm in Germany for Christian's birthday party, I'll upload a video on structure calculation for everybody to watch.
Next week, So there would be a.
Next week will be class. It's still unclear whether I'll do it by Zoom from the ENC or whether Ann is going to teach. But there will be class. And then also I said before you came in, the solution half of the midterm is finished. And Ann is working on the solids part. But it was delayed because I was sick in bed basically from when class ended last week until Sunday.
And what is the expected due date?
Oh, it'll probably be a week or two later.
So since I'm open to the ENC, so maybe 2 weeks will be better than 1 week.
Sure. Other questions? You have a poster?
Yes,
Good.
I'm presenting exactly the same thing I presented during the qualifying.
Well,
Yes.
I'll pretend I never saw it before. I'm presenting a poster too.
Ah,
Are you actually?
Yes.
Or speaking of qualifying exams.
Yeah, yes, I'm trying to, I'm trying to make sure that I actually entered all of my May things before I answer.
So currently it's looking like either the 2nd or the 7th, if you are potentially available.
And what day have I told you to?
The 25th is mine.
Of April,
I have not posted.
but it's gonna have to be in April.
Yeah.
Before April 30th.
I see.
Mine does not need to be April.
So if I agree.
What's yours? Mine, next year.
Ah, yeah.
First year.
We forget.